Good afternoon and welcome to Carlum Cymru sessions. This session will focus on Physics AS Year 12. All right, so if you're on here expecting Year 13, you will find this on the Carlum Cymru website, and there will be a link there because inadvertently we recorded it last night. This particular session on AS Basic Physics Year 12 will be presented by Mr. Ridd from Cynvig School in Bridgend. The session will last around 45 minutes, where the teacher will go through the relevant subject content of the basic physics and kinematics. If you have any questions, please use the question and answer session, and we will endeavour to answer your question during the session. And the session will be recorded, and all recordings with any relevant resources will be uploaded to the e-sgol website in the Carlum Cymru area. So just to reiterate, if anybody's on here, please go to, and you're expecting Year 13, please go to the Carlum Cymru area and there will be a link for you. Okay, welcome Mr. Ridd.
Okay, thank you very much. Okay, so we are going to, as Ms. Owens just explained, dive straight into basic physics and kinematics, okay? So I've got here just a copy of the checklist from the specification that you use, and I'm going to try and get through as much of this as we possibly can in this short session. And we'll be referring back to it as we go to make sure that we're covering it all as well. So to begin with then, the 6 essential base units. Now, these are the units that you're going to encounter in physics at AS and A2, with the exception of really this one here, the CD, or what's called the candela, which is a unit to measure light intensity. But all the other ones you can expect to use. I'm sure you can identify them all. These are known as the SI or base units. SI standing for System International. It's essentially a way of making sure that all the way across the world, we're all using the same units of measurement, and that your meter and my meter are the same length, because that's a standardization and calibration problem. So we know we've got the meter, seconds, we've got A, which you should recognize as amps, we've got K as Kelvin, and then we've got this one here, which is, often used in chemistry a little more, but that is the mole, which pops up in physics, especially in your A2 course, and of course, good old kilograms up the top. You'll notice that they're all lowercase with the exception of these, Kelvin and the amp. Kelvin measurement, or the unit measurement for temperature, and amp is the unit measurement for current. And the reason why is simply because they are actually named after the scientists or the physicists that sort of the units were named after. Anyway, moving on. So those are the base units, and like I previously mentioned, you need to be able to remember those, because there could be marks in an A-level exam for knowing units of measurement, or certainly including them at the end of an answer. Right, moving on then, derived units. So from those base units, we are able to derive other units, and in fact, we can measure anything in physics, and we can talk about the nature of reality and discuss relationships between all kinds of different variables just by using combinations of those base units. So the Newton, for example, is made up of base units, and you might be asked to express a Newton in terms of its base units. So there's 5 little questions there. We're not going to do all 5 of those. I'm just going to pick on 2 of them now. And if you had a question in the exam that said express a Newton in terms of base or SI units, then you'd need to do something a bit like this. So for a start, we think about a formula containing force, because Newton, force is measured in newtons. So for example, the simplest one I can give you is Newton's second law, F equals ma. Then we can break this down into the units of measurement for mass, which is kilograms, and acceleration, which is meters per second squared. Now, in physics and in mathematics, we tend not to do /s to the power of 2 anymore, because we know that 1 over x is the same as x to the minus 1. So what we prefer to write down, and what we tend to write down, is kilograms, meters, seconds to the minus 2. So what that means is that 1 Newton then is equal to 1 kilogram meter seconds to the minus 2. And you can see then how having a unit of measurement like the Newton is in fact a little bit more useful, because you do not want to be saying 55.2 kilogram meters per second squared. It's a little bit of a mouthful. So this is one of the reasons why we have derived units. Now, on to the Pascal. Now, the Pascal is something you will have come across if you've done Young's modulus, and you should have done Young's modulus so far this year. So Young's modulus is measured in Pascal. Now, one way of actually thinking about this, if you remember from stress, okay, which is force divided by area, we can use this formula to determine what a Pascal is in base units. So we know already from the work we just did, well done S, kilogram meter seconds to the minus 2, that's our force, or that's our Newton. And then we can divide that then by the cross-sectional area, and the units for cross-sectional area would be meters squared. Remembering what we did just now, meters squared on the bottom we can write as meters to the minus 2 on top. So then that we can say is equal to kilograms, meters, seconds to the minus 2, and then that's going to be meters to the minus 2. Now, we need to collect like terms and tidy this up a bit, because you can see we've got meters there twice. So we'll say kilograms. This is like meters to the power of 1. So we've got meters to the power of 1, meters to the power of minus 2. That becomes kilograms, meters to the minus 1, seconds to the minus 2. All right. And then we could say that, you know, the Pascal, in terms of its base units, is equal to kilograms per meter per second squared. That would be fine. All right. Moving on. So another thing you're going to have to do, potentially in an exam, is check an equation for homogeneity. Now, what does that mean? It's a bit of a mouthful, I know. Essentially, what we're trying to say when we're looking at equations homogeneity is that it has to be the same on both sides. So this is a very simple and crude analogy, but 5 apples can't equal 5 oranges. What lies on either side of the equation has to be the same. And maybe if I do an example, you understand a little bit better what I mean. So if I have a formula like this displacement formula, which we'll talk more about in a bit when we get on to kinematics. This formula has units of meters on this side, because x, displacement, is measured in meters. So that means that on the other side, we also have to have meters. And let's just check that this equation is homogeneous. So you should know, is initial speed, and initial speed is meters seconds to the minus 1. Now that's multiplied by time, just here, look, okay? And therefore, you should be able to see now that if I've got meters per second times seconds, then these two guys are just going to cancel. Then we're just left with meters, and here we've got a half. Now, we don't really worry about the half. The half is dimensionless, we say. It has no units. We've got the acceleration part now. So acceleration we mentioned was meters seconds to the minus 2 times time squared. Now you see we've got t squared there, so we're going to put seconds squared in here. And once again, you can see that that cancels with that. You won't worry about the half. And once again, all we're left with is meters. So really, what we've got here is the meters are consistent throughout. We've got meters equals meters plus meters. That's okay. We've just got apples all the way through. Okay, so that's an example of homogeneity. Prefixes and standard form. You will be becoming increasingly familiar with standard form, I'm sure, and these prefixes, and you have to know them for your exam. So I've got this little table here. Feel free to go back and have a look at it. I'm not going to spend too much time on it. There's not much to say. You need to know these symbols and exactly what they relate to. Right? This one here, mu. It's called mu, and I always wonder why it's called mu. I think it's because it looks a bit like an M, and it looks a bit like a U. So it's a mu. Anyway, you'll notice maybe as well that one thing maybe to point out that the mega and milli have got the same symbol, or same letter rather. And one thing to note here, of course, is the mega is the capital. So you can think of big letter, big quantity, I suppose. Right, moving on. So if you had something like 1.21 gigawatts, what would that be equal to? Well, 1.21 gigawatts is going to be 1.21 times 10 to the 9. And we don't say 1.21, we say 1.21, but obviously, you know, Dr. Scott, oh sorry, Brown, I should say, and quoted it like that. If anyone can tell me what film this is, I'll be impressed. So what film is that from? Pop it in the chat. I'd like to know. All right, if you know, you're too young, or you wouldn't know what film that's from. So that would do just fine. That's a way of converting. Right. So defining work. This is a little past paper question I found for us here, and the definition of work is really going to be covered probably in more detail by Mrs. Owen when she does her session. But work or work done is equal to force times distance, and just try and remember this for the future, okay? Distance moved in the direction of the force. Now, not crucial for what we're doing right now, but I couldn't leave it blank. Or you could say distance moved parallel to the direction of force. Here is a question, though. This is a past paper question which links to what we've just been doing. Express the unit work in terms of SI base units, kilograms, meters, and seconds. So let's give that a go now. So thinking back to what I said before, you've got to have a formula. Do you know a formula for work done? I hope so. I hope so. Work done, force times distance. Force, we previously said, was kilograms, meters, seconds to the -2. But you know, even if you didn't know that, you might have to go back and go, well, force is equal to mass times acceleration. Mass is measured in kilograms. Acceleration is measured in meters per second squared. That's okay. I can work it out. So we got force, which is kilogram meters per second squared, times distance, which is meters. So what that means is that a joule is actually equal to a kilogram meters squared second to the -2. That is what unit of energy is in SI base units. So let's see how we're doing. We've done the 6 essential base SI units check. We've represented these units in terms of, representing units. So this is the derived units bit. We've had a little look at prefixes as well. We talked about what homogeneity means. Job done. And now we need to move on to the next bit. So we're going to look now at the difference between scalar and vector quantities and give some examples. This isn't too hard, so we're not going to spend too much time on it. What essentially is a scalar quantity? Well, you might know the definition already, and the definition of scalar has just got magnitude and no direction. And then you might already know that a vector quantity has magnitude and direction, but just pause for a moment and think why. And this is what I ask my own students to do. Does it make sense to say 40 meters or 40 kilometers to the west? Yeah, that makes sense. 40 kilometers west makes sense. What about 30 kilograms up or 30 kilograms to the left? Well, that doesn't make so much sense. What about 15 seconds due north? Well, that doesn't make sense. So you've got to understand that there are some quantities that are not expressed or do not need a direction to be involved in their expression. If you can't quite remember the list of vectors and scalars, it is worth pausing to think, right, does it make sense that this quantity have a direction? For example, force. Could I push someone forward? Yes. Could I pull them backwards? Yes. Could I push them from side to side? Yes. Why am I pushing people? I don't know. Maybe I shouldn't be. But just think in those terms, and sometimes your intuition won't let you down. Now, you'll notice here there are two quantities which are really similar, distance and displacement. Now, distance and displacement are very, very similar, but there's a crucial difference. So I'm going to give you a simple analogy to sort of highlight that now. Let's imagine at break time, you left the classroom, you went down to the hall, got some food, and came back to the classroom. All right, probably to do some extra work or something. Then the distance you would have covered is from the classroom to the hall to get some food, and then back again. It's the total distance. But your displacement is how far you are from your original position, where you started from. I mean, you know, this is my original position, I can go up, down, left, right, over here, down, down. I can do all that distance, but actually my displacement is this distance here. How far I am away from where I started. So that's the difference between distance and displacement. Now, speed and velocity, well, speed is equal to distance over time, and velocity is equal to displacement over time. Sometimes we say that x over t. So these can be very, very different. If you think about a cyclist going around a track, right? Think about a cyclist going around a track. After he completes one lap of a track, he will have essentially arrived back at the same point. So his displacement, x, will equal 0. So technically, the velocity of a cyclist who completes one lap of a track will be 0 because the displacement is 0. Whereas the distance will just simply be the magnitude of the size of, you know, how far they travel. Maybe the track is 400 meters. If they've gone 400 meters round, then it will be a different question. The speed will be a different answer. It'll be the distance over the time. So yeah, I'm not going to dwell on these too much more. Acceleration, force, weight, momentum, all vectors. Time obviously only has, you know, magnitude, energy and mass. All scalars. I'm not getting into the whole antimatter thing. I'm not having that discussion now. I just tell my students to leave if they bring it up. Okay, so vector addition now. When we're adding together scalars, it's so easy. 5 kilograms plus 6 kilograms is 11 kilograms, all right? But what about if we are adding together some vectors? Well, let's do a simple example to begin with. What if I have 5 newtons, and to that I'm adding, say, oh, I don't know. Sorry, I'm adding 2 newtons. That's easy. I'm sure you haven't got a problem with that. That's 7 newtons. So adding together those two vectors is easy. All right, well, what about 5 newtons? And to that, we're adding 2 newtons. Now, this is different, isn't it? This, I'm sure you're aware, the answer is going to be 3 newtons. Oops. 3 newtons. All right. Now, really, what we can think of here is the fact that the 5 newton and the 2 newton force are in opposite directions. And when we add vectors together, we add them together point to tail. So in the top one, we add in the point of one to the tail of other, and that's fine. In this one, it's kind of like we're adding the point of one to the tail of the other, and in doing so, sort of subtracting from it. Right. What about, though? This is all very pedestrian and straightforward. What about the situation where we get our 5 newton in that direction? No, sorry. No, that's skipping ahead a little bit. Hang on. What about if we've got our 5 newton force in this direction plus our 2 newtons. This is supposed to be a 5, by the way. That's our 2 newtons in the vertical direction. What do we do now? What's this going to be equal to? Well, what we need to do then is remember we've got to go point to tail. So once again, we do our first vector, we add it to our second vector, point to tail. And now we've got to work out what we know as, or what we refer to as the resultant, which is this. It's what closes the shape. It's what's left over. It's how far we are from our starting point. So to work that out, you know, you should already know by now, or you should be aware that it's just a simple mathematical problem. So x here, our unknown, is our hypotenuse, and x squared is equal to 5 squared plus 2 squared. Right, and 5 squared plus 2 squared, as we all know, is equal to, let's see, 25 plus those 29. Okay, so it's a slightly awkward number. And then, of course, x then is equal to the square root 29, which is 5.4. So that's not too bad. So we added together 2 vectors now, which are in different directions, but they were at right angles to each other, which makes things to some degree easier. But this is a vector, and as such, because it's a vector, it needs to have a direction. Now, in your exams, I mean, I just marked a bunch of papers from my own class, and there are marks being lost because they might find the magnitude out, but not the direction. Now, if you do your little diagram like this, and you label it with the theta, then when you calculate theta, any examiner is going to know exactly what angle you mean and what direction you're talking about. So we're going to go ahead now and work this out and say that the tan of theta is equal to the opposite of the adjacent. Right? This would be the op, this would be the adj. So that's going to be 2 over 5. And then theta, if you do the trig, comes out as 22 degrees. All right. Well, let's push it on now and see if we can make it even harder. What about if we have our 5 Newton vector off at an angle like that, and now we're going to add it to 2 Newtons in this direction like this? What are we going to do now? Well, what we need to do now is resolve a vector. To answer this question, we have to resolve a vector, because if I put these 2 together, look, right, let's say I'm thinking, right, I'll put these together, point to tail, the 2 together like that. What we end up with now is not a right angle triangle, okay? And that's going to make us sad and angry. So we haven't got a right angle triangle. We can't do that method we just did. We need to resolve a vector, and let's have a look at doing that. So with resolving a vector, in general terms, what we do is if we have a vector which is x, we look at that and realize that in fact that diagonal vector is to some degree contributing something horizontally, and it's also contributing something vertically. It has both a horizontal and vertical projection. We can work those out. I mean, if I wanted to, I could put that on this side. Now, I'm going to mark an angle theta there. The horizontal component of this is going to be x cos theta, and the vertical component is going to be x sine theta. I go into it in more detail, but given the amount of time that we've got, I think we should just push on. Suffice to say this, though. The component, and this is the horizontal component here, the x cos theta is the horizontal component. The component that has the angle between itself and the vector will be the cos component, and then the other one's the sine component. That's just an easy trick to remember it. So if we go back to our initial problem now, I can take this 5 Newton vector, and as long as I know the angle, I can work out and solve this problem of vector addition. So what I'll do is I'll say 5 Newtons now, and we'll work out what the horizontal component is. Whoops, sorry. It's happening a lot tonight. I do apologize. And the vertical component. Now this horizontal component then is going to be 5 cos 30. And the vertical component is going to be 5 sine 30. Now, when we work those out horizontally and vertically, what we end up with is that the vertical component is equal to 2.5. And the horizontal component is equal to 4.3. And now we can add our horizontal and vertical components together. Now, if I think about this problem vertically, first of all, then we have only got one vertical component. If I go back up here to begin with, there's only one vertical component, and that comes from that 5 Newton force. So that vertical component we know is 2.5. So vertically, we've got 2.5 newtons. Horizontally, though, we have actually 2 things to add together. Because horizontally, we have 4.3, that's here, from the 5 Newton force. But also, we've got this 2 newtons to deal with as well. Now, I've done -2 because the 2 is going backwards. And in fact, one thing you need to remember, it's a lot to cover in 45 minutes. I'm trying my best, guys, I promise, is that we have got to remember our quadrants, I think they call it in mathematics. So anything up here, is in the y direction is positive and the x direction is positive. So anything here is all positive, isn't it? And then, of course, you can have something down. If I had a vector down here, then it is positive in the x direction. This one is positive in the x direction, but negative in the y direction. So it's something you've got to watch out for. Such a vector as this will have a negative horizontal component and a negative vertical component. And a vector such as this would have a positive vertical component and a negative horizontal component. So you've got to watch out for that. That comes then to 2.3 newtons. And now we're almost done. Tricky one, but we're almost done. So we've got to now add together these horizontal and vertical components and turn it back into a vector. So let's give that a try. Vertically then, we know that we have got 2.5. And horizontally, we know that we've got 2.3. Therefore, we can just close that up. It doesn't matter which order you add them in, point to tail. You could have started with the 2.3 and then gone up with the 2.5. It wouldn't make any difference. It'd be the same. My mark on this angle is what I'm going to work out. We're going to do the whole Pythag thing, even though he wasn't a very nice guy. Look him up, he wasn't a nice guy. 2.5 squared. Thought a lot of himself, he thought an awful lot of himself. And that gives you 3.4. Okay, so that is the magnitude then of our resultant, 3.4. And then the tan of theta is going to be 2.3 divided by 2.5. And then we're going to get the theta is equal to 42.6 degrees. So that is how you can add up vectors that are, jaunty angles to each other. We call coplanar vectors, 2 coplanar vectors. You have to resolve into horizontal and vertical components or perpendicular components. And in doing so, then you just add together all the vertical ones, you add together all the horizontal ones. Be careful of the signs, and you'll be just fine. And you can add together like loads. Sometimes I give my own students like problems like this. So be grateful you're not in my class, because I'll give those numbers and angles and I'll say add them all up. Right then, so we're going to say that that is done, that is done, that's done, that's done. So addition and subtraction of coplanar vectors and perform mathematical calculations limited to 2 perpendicular vectors. Job done. How to resolve a vector into 2 perpendicular components, that's something we just covered. The concept of density and how to use it, oh, you know what, I spoiled it for myself a little bit. So we're going to say that those done so far, so we're making pretty good progress. So I was going to leave that up there. That was the plan. I was going to leave that up there and say, what do you think the next bit's about? But I've blown it, really, truth be told. So yeah, It's that old riddle, isn't it? What's heavier, a ton of feathers and a ton of bricks? And because you're super smart people, you are, you know that the answer, of course, is that neither is heavier. And that what we're really talking about is the difference between the two, and that is density, right? So we're really talking about density. Now, I'm not going to spend ages on this because it's not a particularly difficult concept, but I am going to spend a little bit of time looking at this question because it kind of pulls together a few of the things that we've been doing. So, on first glance, this might seem all right, but actually this is a pretty hard question. The material has a mass of 800 grams and a volume of 6,000 centimeters cubed. Calculate the density in kilograms, okay? Now, the first thing we need to do is think to yourself, right, well, if we want the density in kilograms, all right, per meter cubed, which incidentally does make sense, isn't it? Because density is equal to mass divided by volume. When you know that mass is measured in kilograms, volume is measured in meters cubed. So actually, kilograms per meter cubed, you can derive that unit for density based on what we've already learned. So the density then is going to be the mass. Now, if we want it in kilograms per meter cubed, we've got to be careful here because we've got 800 grams. What's 800 grams going to be in terms of kilograms? Well, we're going to divide by 1,000. That's going to be 0.8 kilograms. Divided by, here we go, the volume, 6,000 centimeters cubed. Is that in meters cubed? No. This is where you start to panic, you get hot sweats, it's a horrible time because what you've got to do now is convert 6,000 centimeters cubed into meters cubed. Let's do it this way, right? So we're going to take a little aside here. 1 centimeter is equal to 1 times 10 to the minus 2 meters, okay? 1 centimeter is equal to 1 times 10 to the minus 2 meters. 1 centimeter squared is equal to 1 times 10 to the minus 2 all squared. All right, now that is equal to 1 times 10 to the minus 4, because 2 times minus 2 is 4. That's what you do with those powers, meters squared. And then finally, 1 centimeters cubed is equal to 1 times 10 to the minus 2 cubed. So that's equal to 1 times 10 to the minus 6 cubic meters. We're nearly there. So therefore, 6,000 centimeters cubed. If 1 centimeter cubed is 1 times 10 to the minus 6 meters cubed, 6,000 centimeters cubed is equal to, so it's 6,000 times that number, isn't it? So it's going to be 6,000 times 10 to the minus 6 meters cubed. We can tidy that up, can we? So we can call that 6 times 10 to the minus 3. 6.0 times 10 to the minus 3. Move the decimal place 3 places. All right. Meters cubed. All right. So if we do that, then now we're able to answer this question, and we can just pop this on the bottom because we know it's in meters cubed. 6.0 times 10 to the minus 3. You put that in, you end up with 133 kilograms per meter cubed. Does it float? Put your answer in the chat box. Does it float? I'm sure Miss will confirm it for you. Right. Kinematics, how are we doing for time? 15 minutes left. I think we can make a little dent in this, okay? So we're going to move on to kinematics now. You'll notice that I didn't quite get as far as moments, all right? But Mrs. Owens is going to cover that in a later session. So we're going to leave that for now. So watch this space. Kinematics then. What is meant by displacement? Mean instantaneous values of speed, velocity, and acceleration. Okay. Now I'm going to go quickly, but you can always watch this back. Here we've got a little graph showing, you know, how we can interpret different motions on different graphs. Now you've got here steady speed, which is shown by a diagonal line on a distance line graph. Okay. And then stationary, well, it makes sense, doesn't it, that we've got stationary here, the object isn't moving, the distance isn't changing. And then finally, we've got this diagonal line here going back in the opposite direction. This is a steady speed returning towards the start. The gradient of the line is proportional to the velocity. So the steeper the line is, the greater the velocity will be. Then you'll notice this blue line here. See this guy here? Now this blue line is showing that the gradient is increasing as time goes on, which is also then indicating to us that this object is accelerating, because the gradient is going up, it means the velocity is going up, and if the velocity is going up, then that means the object is accelerating. Now, if you needed to work out mean velocity is total distance over time. So mean vel is total distance over time. Okay. And if we work out the total distance over the total time, in this case, it's 70 divided by 8. 70 divided by 8 is 8.75 meters seconds to the minus 1. Okay, so that's what we mean by average speed then, okay, or mean velocity. All right, it's the total distance over the total time. But what about if we had to work out instantaneous velocity? Maybe a question said instantaneous velocity at 6 seconds. How would we do that? Well, first of all, you've got to find 6 seconds, and we've got to remember that, yeah, sure, the average velocity is like, you know, what the velocity is over the whole journey, but we already said that the velocity at the start is lower than the velocity at the end. So what is the velocity at any given point, in this case 6 seconds? Well, we can work that out by drawing a tangent to the curve at that point. So we draw a tangent to the curve, and then it's, again, now it's a simple speed equals distance over time problem. Okay, that much hasn't changed. We look at our change in y over our change in x, so change in distance over time. In this case, it's something like, looking at that, you can, yeah, this is about 58. Whoa, that's supposed to be an 8. This is about 58. This is 5. So what we end up with is v is equal to 58 over 5, which is 11.6. That's how you work out instantaneous velocity. Bouncing ball. Let's see if we can get this done now. So bouncing ball, what does that look like on a distance time graph? What does it look like on a velocity time graph? And what does it look like on an acceleration time graph? Well, first of all, if we were to drop a ball, its distance, okay, would increase. And remembering that the gradient of that line is going to tell us a velocity. So initially the gradient would be 0. Okay, so we'll just do it like this for now. So the gradient would be 0. Then it hits the floor, and it experiences a rapid change in its velocity. It'll go from a high negative velocity, as it is here, to a high positive velocity, and it'll do this. Now, strangely, it actually ends up looking like a bouncing ball. That's not going to help you anymore, right? That's only going to help you once. Now, with a velocity time graph, what happens? Well, with a velocity time graph, if we were to drop that ball, then its initial velocity would be 0. Then as it falls, its velocity increases at a constant rate, which looks like that. That's a steady acceleration, and that acceleration, as you know, is minus 9.8 meters per second squared. Then when it hits the floor, it has a rapid acceleration in the opposite direction. So it has a constant acceleration downwards, and it has an ever increasing larger negative velocity. When it hits the floor, it undergoes a rapid change in acceleration, or change in direction, while it's in contact with the floor. And then it jumps up to a quite high positive velocity. Now, as soon as that happens, it starts to, once again, slow down. This point here is known, this is the maximum height. This is going to be where the velocity is 0. Because remember, when it comes to the top of its bounce for instant in time, it's going to be stationary. And then once again, then it's going to start to repeat and fall down. Again, we've got another bounce there. And the other thing as well is, as successive bounces happen, it loses energy each time. Okay, I'll talk about this for a lot longer, but I thought I'd just pop that on quickly. And then with this one now, acceleration finally, what we'd end up with here is a large negative but constant acceleration. Then we would have a very rapid positive acceleration where it bounced, which would probably look like, I can't really draw on the graph, but it would be a succession of, it would essentially be little, it'd be a lot of these with tiny little blips, right, where it's in contact with the floor. But yeah, constant acceleration anyway with that. Driving equations of motion. We've got 4 minutes left. Let's give it a go. Okay, so to begin with them, we got 2 equations of motion, which you already will be familiar with from GCSE. U plus V over 2. We'll do this one thing, driving equations of motion, and then we'll call it a day. We're going to call that equation 1, and then we've got this other equation from the GCSE for velocity. We're going to call that equation 2. Then we go into, we're going to sub 2 into 1. And that means that basically where I see this equation now, it's going to rearrange the equation number 2. I'm just going to rearrange equation number 2. So it says T is equal to V minus U over A. And where I see T in equation 1 up here, I'm going to write this in instead. So now I'm going to say S is equal to U plus V over 2. And instead of writing down T, I'm going to write down V minus U over A. Now, if you start tidying that up, what you end up with is UV, if you expand the brackets out, minus UV. Oh, gosh. All right, UV minus UV. Minus U squared plus V squared all over 2A. Now that cancels with that, and you end up with S is equal to V squared minus U squared all over 2A, which is equal to S is equal to, yeah, that's fine actually, V squared minus U squared is equal to 2AS. All right. Now S, I should say, is interchangeable with X for displacement. So X or S for displacement mean the same thing. And then finally, then to derive the last equation of motion, we are going to look at rearranging equation 2 again. So I'm going to rearrange equation 2. V is equal to U plus AT. And what I'm going to do there now is, once again, I'm going to sub that into 1. I'm going to sub into 1. And now I'll use X this time. I do apologize. I should use X more. X is equal to U plus AT. So where I see, you know, and I'll just remind us what equation 1 was. Equation 1 is X is equal to U plus V over 2 times T. So where I see this now, where I see, sorry, V, okay, I just substitute that in, U plus AT, and then that equals 2 UT plus AT squared all over 2, and then that simplifies down into UT plus a half AT squared. And those are your 3 equations of motion. Now, I think in terms of how far we got, we definitely got that far. Yeah, I think so. We could say the properties of distance time graphs and velocity time graphs interpret speed. And I think we'll probably say that we got no further. We did derive the equations of motion, but I think that's the end of the session now. Yep. So I'd like to thank you all for coming. I hope that was helpful. And if we didn't pick up anything here, we'll pick them up in subsequent sessions, I'm sure. So well done to those who came.
Okay, thank you very much, Mr. Wood, to a synopsis of basic physics and kinematics, and hope to we are joined by you next time. Thank you very much.
Bye.